So what are we doing right now? We're finding general rules to find closed form rate of change functions from closed form accumulation functions. Okay, and so this is what we have so far. Rate of change of a constant is 0. Rate of change of a constant times a function is that constant times the rate of change of the function. The power rule says that the rate of change of x to the n is n x to the n minus 1. The rate of change of the sum or difference of functions. We said that's exactly what we would hope for. We love this result, that it's the rate of change of the sums of the individual functions. Rate of change of radical x, 1 over 2 radical x. Rate of change of b to the x, an exponential function, is b to the x times natural log of b. And then from that one, the very special case of this is that one base that makes that ln of the base 1, so that the accumulation function and the rate function are the same. So that's the only function like that exists, where your value, your total value of accumulation is also how fast the accumulation is changing at any x, okay? That's a really cool function. And we like the derivative, right? So we like this rate of change. It's easy. Okay, and then last time we talked about this one, and you had some examples in homework, the rate of change of a composite function. And so we want to, from here on out, when we solve these composite functions, we're going to talk about the exterior function and the interior function, because that will frame then how we do the rate of change. So the way I have it here, what is the exterior function? Which function is the exterior function? G. And then the interior function is F. So the rate of change then is the rate of change of the exterior function, the big picture function, with respect to the interior function as it is. You're not going to change that. It's not the rate of change of F. And it's not X. It's F. Okay? So it's going to be the rate of change of the exterior with respect to the interior, keeping it as it is. And then, this is the chain part. We're going to chain on times the rate of change of the, what's F? Interior function. Okay? And then that can be flipped either way. So this is kind of like the outside in approach. You start with the exterior and you work your way in as you go left to right. But you could do it inside out too. You could start with rate of change of the interior times rate of change of the exterior with respect to the interior. That would be kind of like working inside out. So both ways are possible, and for some we'll do it one way, some will do it another. It's just changing the order, okay? Questions on what we've got so far? Okay. So here is, could you guys help me pass these out? Sorry. Here's a more exhaustive list, similar to the list we had on the last screen. Maybe from the outside. Oh, that doesn't matter. Okay, and so then, okay, so here's a more exhaustive list. This piece of paper is just for class today. Okay, there's one that's cut off. We're not going to use that one that's cut off. You're going to get this as an electronic file on Blackboard, okay? Eventually you'll have it. This is just for what we need for class today, okay? So I'm going to point out some here that we did not, all these that I showed on the previous screen, we derived. We showed where they came from. So now we're going to just use them. So for instance, the rate of change of the function sine x is cosine x. So this is an important one. We'll see it a lot. Similarly, the rate of change of cosine is the opposite of sine. So if you have the cosine function as your accumulation function, its rate of change function is the opposite of sine function. Tangent is secant squared. What else? Okay, so we did exponential. What about log functions? The log base b of x, if that's your accumulation function, the rate of change function is 1 over x times ln of b in the denominator. And then a special case of that is the natural log. The natural log function, its rate of change function is simply 1 over x. So these additional 5 we're going to see later in class today. So I want to just point those out. You have that piece of paper as a reference now. And eventually so the mastery exam is then learning to use these rules and then use them in combination. So starting early next week, we'll start to see some problems that get kind of algebraically very complicated because we're using several rules at once in the same problem. So we're going to build up to that. Okay? In order to do the complicated ones, though, we have to have the basic ones memorized. So by the time the mastery comes around, you'll have all of these memorized. But we're halfway there, right? We're halfway there. So it's not bad. There's not much more to do. Okay. Questions on that? So these 5 that I've circled, you've got them on your sheet. These are going to be common ones. We're going to see them in class later today. Oh, and then you read about the new notations, right? Or the other notations for rate of change functions. What was the name of this notation called? Differential notation. Differential notation for finding the rate of change. And then the other one was prime notation. But all of those notations are still referring to the rate of change function for the given function. Okay, the rate of change function, which we're also calling like R sub f or R sub g, whatever that is. Okay. So, chain rule. Let's practice some chain rule problems. Remember we talked about it's the rate of change of the exterior with respect to the interior times the rate of change of the interior. So let's do a couple of these together. So first we have to recognize that we have a composite function. So here's cosine of natural log of x. So we recognize that that is one function as an interior function and plugged into an exterior function. So what is the exterior function? Just the exterior function. Just the exterior function is cosine. So therefore, if we're finding the rate of change of this, we're going to do the rate of change of the exterior with respect to the interior. So rate of change of cosine with respect to natural log is negative sine of, all right, so the biggest all right, and then that's that first part, times the rate of change of the interior function, which we just said is 1 over x. There's your rate of change function. That's using that chain rule. Okay, what's a really common mistake that students make? Negative sine of 1 over x. So when you're doing the rate of change of the exterior function, you leave the interior as it is. And we saw why that was true in last class. Review the video. But don't do negative sine of 1 over x. Like thousands before you have tried, okay? Don't do that. Okay, next one. Log base 5 of sine x. Exterior function is? Log base 5. Rate of change is? 1 over? Okay, so it's going to be 1 over the interior function. Instead of x, it's going to be 1 over the interior function times natural log 5. So that's this first part. Times the rate of change of the interior function. Cosine x. Stop me if you have a question. Are we good? Does it make sense? Okay, I'll just let you loose on these next ones. So you're either making progress or you're getting help. Go. You're either making progress or you're getting help. Okay, so for this first one, 2 times. So the exterior, so what would you call the exterior function there? What is that exterior function for that next one? Something squared, right? Something squared. So the derivative or rate of change function is 2 times that thing to the first, leaving the inside as it is, and now times the rate of change of the inside, which is 1 over 2 radical x plus what? 0. Not 3e squared. Why not 3e squared? It's not x cubed. It's not our independent variable cubed. It's a number cubed, which is just gives you a number. So it's just 0. So you wouldn't need this. Just 1 over 2 radical x. Questions on that one? Okay. What's the overall structure of this one? What's the overall structure of this next one? So the overall structure is what? A composite function? No, so the overall structure is a constant multiple. Constant multiple. And how do we handle a constant multiple times a function? Rate of change of the constant is 0. Right? No, it's multiplied, right? It's not, so it's not 0. You just hold on to it, right? It's just going to be 6 times whatever the rate of change is. Now we've got this thing, and this is a composite function. Exterior function is what there? Exterior function. 7 to the something. 7 to the something. Rate of change is 7 to the something. Natural log 7. That's our exponential, right? So the exponential rate of change is just, you repeat it, right? 7 to the something times L on 7. Now, by the chain rule, we need the rate of change of the interior function, which is secant squared. I gave you on the list, right? How are we doing? So questions. They're going to get a lot harder. We got to make sure we got the easy stuff down. Yeah. So you have to see, first of all, you have to see this as a constant times a function. Do you see that much? So hold on to the constant times the rate of change of the function. So then you have to see the structure of this, which is basically 7 to the x with tangent x plugged into it. 7 to the x, so x is now your independent variable, but then that's a function. So this is a composite function. Your interior function is tangent, and your exterior function is 7 to that something. So your g function is 7 to the something, and your f is tangent. You see it now? And then, so then it's the rate of change of g, which is the rate of change of an exponential function. And that's it right there, 7 to the something times ln of 7, times the rate of change of the interior function, which is going to be the rate of change of tangent x. Better? Last one, exterior function. What's the rate of change of square root? 1 over 2 square root. What goes under here? As is, right? As is. Rate of change of exterior with respect to the interior as it is. So you leave it as it is. 6 times 7 tan x to the tan x minus cosine natural log of x. Then, what's left? Times the rate of change of the interior. What is the structure of the interior? Not composite. What's the structure of the interior? Difference. Rate of change of the difference is? Rate of change of each. So the whole thing, so there are composites involved, but the whole thing is a difference. Do you see that? Yeah, the whole thing, the structure of the whole thing. So what we're going to do, rate of change of the first minus rate of change of the second. What is the rate of change of the first? What we did here, which was constant multiple and chain rule. So I'm just going to take this right here. So it's what we did here. This is the rate of change of that. So it's going to go there. See that? Minus what we did up here. The rate of change of cosine of ln of x. So that thing is going to go there. Now I'm not just doing this to save writing. There's a point that when things get multi-layered, you don't change the rules. You don't change the rules. You do the rate of change of the interior, right? We're working on the rate of change of the interior part of this, which is everything under the square root. So when we're working on the rate of change of this, well, we look at that as its own separate problem. What's the rate of change of that? It's all of this by the chain rule. So that's going to go there. And then minus, what's the rate of change of this? It's all of this by the chain rule. See? So when you use the rules in combination, you still follow the rules. You still follow the rules. You don't say, oh, because I'm in the middle, I'm going to do it different. No. I get to the rate of change of the interior function, and now I come to 6 times 7 to the tangent x, and I do the rate of change of that. And then I get minus cosine natural log of x, and I do the rate of change of that, which was what we did before. So that rate of change function is this whole thing. Questions on the last one? Yeah.
Instead of like putting like the 6 times 7 tan x minus that whole thing on the bottom, can we just put it to the negative 1/2?
Yeah, so this is the same as this thing to the negative 1/2, if you prefer that. Yeah, that's fine. 1/2, that thing to the negative 1/2. Same, it's the same. Yep. Other questions? We good? Okay. So this is a foretaste of what's to come next week. They're going to get a lot more complicated than this, though. Okay, so this is just a foreshadowing. Okay, so we have not yet dealt with products or quotients of functions. Products or quotients of functions. So here's 2 functions. And suppose k of x is f times g. F times g. So, question is the rate of change of k the rate of change of f times the rate of change of g? Wouldn't it be nice, right? Wouldn't it be nice? But it is not. It is not. It is something else. Similarly, here's a new function h, which we made by taking the quotient of f and g. Is the rate of change of h the rate of change of f over the rate of change of g? Wouldn't it be nice? But it's not. Something else. Okay? So this kind of approach works with sum and difference. Right? With sum and difference. Yes, the rate of change of the sum is the sum of the rate of changes. But it does not work for product and quotient. Though it's been tried by thousands of calculus students in the past. They got the wrong rate of change function when they did something like this. So don't do this, okay? So let's talk about what is the rate of change of a product. So here is a product of two functions, f times g. And I'm interested in, let's use prime notation here. That's times, not composite. So if we were going to figure out what is this rule for the rate of change of a product of functions, how do we start? Everyone in the room should be able to write it down. How are we going to start doing this? So let's see. Let me use differential notation. Maybe it would be easier to see. Yeah, that's better. Okay, so using differential notation. I want everyone to start. What would be the first step to figure out or to derive what this rule will be for the product of two functions? Write it down. Everyone should be able to write this down. Show me. Show us. We're going to look over your shoulder. I want to see. First step. No. First step. If we were to try it, you don't know anything about the rate of change of a product. You've never had calculus before. How are we going to figure it out? Very close. Almost had it. Show me the first step. Yeah. Yes, there you go. Good. All right, some people are getting it. So we're going to use what we trust. What do we trust? Our trusted rate of change formula, right? The function at x plus h minus the function at x all over h. That's the trusted form for a rate of change function. That's what you should have. Okay, so how are we going to do this? Well, here's what we do. In the numerator, we subtract fx times g of x plus h, and then we add it. So the effect of this is doing what? Well, yeah, so we just kind of stuck 0 in there in the form of negative f g of x plus h plus f g of x plus h. So that's legal, right? Because you can add 0 to something and it's still the same, right? Okay, why do we do that? Because it works. Okay? So mathematician in the past was, having a ball at his desk, moving symbols around, and was able to kind of figure out that this will get us to a a rule for finding the rate of change of a product. So if you notice, what happens here is we're going to group, by grouping these two together, you notice a common factor. What common factor do you notice there? G of x plus h. And then we're going to grab the positive thing that we put in there, and we're going to group those two together. And we have a common factor of f of x. So I'm going to factor out of the first one, I'm going to factor out the g of x plus h, and the f of x out of the second. And we get this. And then we notice something. We notice something familiar here. What is that? It's the rate of change of f, right? Isn't that the rate of change of f? And then also, over here, take that h, combine it with this over here too. Rate of change of g. And that pretty much we're pretty close now. So we're going to gather that rate of change of f together times g of x plus h, and gather that rate of change of g times f of x. And then if we want the exact rate of change, what do? Let h do what? Get really small. When h gets really, really small, we get just g of x, times the rate of change of f, plus f times the rate of change of g. This is our rule for finding the rate of change of a product of two functions. So, again, notice that it is not the rate of change of f times the rate of change of g. Okay, so here's prime. Just watch the video. If you want to copy that down, just do it. Grab the video. We don't have time. I can't wait. Okay, just watch the video. You're fine. Just leave some space. Everything will be all right. The rate of change of a product of functions is what then? It's the first times the rate of change of the second plus the second times the rate of change of the first. So this is how you can think of it. It's the first function times the rate of change of the second plus the second times the rate of change of the first. Okay? Addition is commutative. You can switch addition. Multiplication is commutative. You can switch multiplication. So this is really hard to mess up if you've got the overall structure of it. So you can switch the orders of things. Just as long as you have one of the functions times the rate of change of the other, and then the reverse added on, right? That's what you need. So let's practice. Here's a function. Notice what's the overall structure of this function f? What's the overall structure? Is it composite? Is it power rule? Is it a quotient? It's a product, right? The overall structure, this is always the first question we're going to ask, especially when you get to the more complicated ones. What's the overall structure of the function? The overall structure of the function is product. Therefore, we're going to apply the product rule, the one we just did. And the product rule says that we're going to need, okay, we already did that. It's product. We're going to need to see this as two functions multiplied together, and so we're going to need the rate of change of each, right? And in the end, if it's a product, the solution is going to be of this form. First times the rate of change of the second plus second times the rate of change of the first. Prime notation, right? Prime notation for rate of change. So all we need then we only have two things that we need. Rate of change of g, which is 8x cubed, piece of cake. Rate of change of h, which is 6x, piece of cake. Now we just write it down. We just follow the rule, right? Follow the rule. G of x is 2x to the fourth minus third times rate of change of h, 6x, plus h of x times rate of change of g. And we're done. Questions on this pretty simple example applying the product rule? Does it make sense? We good? Okay, what about quotient? We said, now for this one, we're going to actually use the product rule to derive the quotient. We're going to use the product rule to derive the quotient. So how can I write this quotient, f over g, as a product? F times g to the minus 1, right? So now we're going to apply the product rule, but then notice that when we get to the rate of change of the second function, what rule will we have to apply there? Power rule, but also chain rule. So when within this product rule, we're going to have the rate of change of the second in there. When we get to the rate of change of the second, it's really the chain rule, because we have a function raised to the negative 1. So we're going to have to, when we get to that part of the product rule, we'll have to use the chain rule within the product rule. Okay? So here's the first times the rate of change of the second, plus the second times the rate of change of the first. That's just direct application of product rule. Okay, so can you go ahead and before I reveal it, let's do this. This is kind of the only, that right there is the only real tricky part left. So can you do just that? So what is the rate of change of g of x to the negative 1? What is the rate of change of g of x to the negative 1? And what rule are you applying there? Chain rule. Chain rule. Exterior function is? To the negative 1. To the negative 1. Interior function is? G. So we're going to do exterior with respect to interior times rate of change of interior. So that looks like that, right? Rate of change of exterior would be negative 1 g to the negative 2 times the rate of change of g. Everything else is straightforward. Questions on that? Anybody have a question? Okay, so then with some algebra that we don't want to take the time for, we make it into this. Okay? So that these are equivalent by following good algebra. And so what do we have? We get the denominator times the rate of change of the numerator minus the numerator times the rate of change of the denominator all over the denominator squared. This is our quotient rule. Quotient rule. There's the rate of change function notation. The rate of change notation instead of the prime notation. Both mean exactly the same thing. And there's prime notation. So here they are. There's a variation on the prime notation. Okay, so there's a little song you can sing to help you here. Okay? Like the 7 dwarfs. Low d high minus high d low over low squared. Low is referring to the denominator function. Okay, so you're saying, you say low means the function in the denominator. So low in this case is gx. Low. It's low, right? It's low. And then high means the numerator's function. So high is referring to f of x. So if we use low and high, then we got low d high, like the differential idea, right? Low d high minus high d low over low squared. Okay, now order matters. If you change subtraction, you get something different. You get the opposite. So now this in the numerator, what comes first matters. You have to have low times the rate of change of high first, and then minus high times the rate of change of low, over low squared. All right, so really then, if you can just remember this first part, that's all you really need. Because it's low d high, it's going to be minus, then high d low, and then over, just remember low squared. Questions on the quotient rule, which is harder to memorize than the product rule, but you do you do 5 or 10 of these, and you got it, okay? All right, so let's apply it here. And we said that the rate of change of on your sheet, this is the rate of change of tangent is secant squared, right? So let's prove that. So we're saying that the rate of change of tangent is secant squared. We'll prove it using the quotient rule, okay? So we'll need to know what tangent is. Tangent equals sine over cosine, and then eventually we're going to need sine squared plus cosine squared equals 1. So by finding this rate of change function, we're really finding the rate of change of this ratio, because that's the same as tangent. See that? So let's, instead of doing tangent and going tangent of x plus h minus tangent of x over h, let's instead do the derivative of sine over cosine and apply the quotient rule. Quotient rule says, how does it start? And they all sang in chorus. Low d high, low d high, low d high, or the rate of change of the numerator, which is cosine x, minus high d low, high d low, or rate of change of the denominator, all over low squared, which is just the denominator as it is squared. What do you get in the numerator? This right here, cosine squared. This is going to be plus sine squared. Numerator is 1 over cosine squared x, and 1 over cosine is secant. By definition, secant is 1 over cosine, so 1 over cosine squared. Got it. Rate of change of tangent is secant squared. Questions on applying the quotient rule? All right, let's try one here. So let's try a harder one. First thing we do, identify structure. Identify structure first. What's the overall structure of this function g? It's a quotient. Therefore, the overall structure of our rate of change function will be using the quotient rule. If the overall structure is a quotient, your overall approach to the whole rate of change function will be quotient rule. So what we need what is our, let's write it. Low is what function then? And then what is then d, what we're calling d low? Okay, so we're going to do the rate of change. So we're going to put the pieces together. We're going to do all the pieces first. We know we're going to need the rate of change in the denominator, or d low. We know we're going to need the rate of change in the numerator, or d high. And then after we have those, then we can set up the quotient rule. So we're going to think big picture quotient rule, and we're going to get our our parts first and then set that quotient rule up. Okay? So, we're currently working on the rate of change of this right here. So 3 to the radical x. What do we need for that? Chain rule. That is what? Square root of x as an interior function, and the exterior function is 3 to that. It's exponential. So therefore, the rate of change is 3 to the square root of x times natural log of 3 times. So that's the rate of change of the exterior. Then times the rate of change of the interior function. So that right there is the rate of change of 3 to the radical x. Rate of change of exterior with respect to interior times rate of change of interior. Then minus, look at you, so what is the negative cosecant x times cotangent x? What's that? So that there is the rate of change of the denominator, or d low, right there. Okay, hi. That function is, that's our numerator, log base 2 of 4x. So we need d high, or the rate of change of that function. So we need to apply a log base b rule. So that's going to be, looking at your rules there, 1 over 4x, natural log of the base 2. Are we done? This, notice this is another composite function, right? It's 4x plugged into log base 2 of something. So by the chain rule, we also need the rate of change of 4x, 4. Okay, can you do it? So now, so what is our quotient rule? Is low d high minus high d low over low squared. Low squared. And it's off to work you go. Do it. So finish it. So you're ready to finish it. Don't do any simplification. Just follow the quotient rule, and you're got the rate of change of g. So what do we do? What's first? Times d high, this thing here. I didn't leave enough room. Okay? Need some room here. Okay. Then what? Minus, one guy's got it. Is everyone following this? Minus high, which is log base 2 of 4x, times, yeah, so that I'm not gonna rewrite, I'll do it in red. This thing right here, that was our rate of change of the denominator, or d low. Which squared? Just, yeah, so the original denominator squared. And that's it. Don't simplify anything. Anybody have a question on getting that set up? So primarily for the homework for Monday, it will be from that list of 150. I'll pick out maybe 25 or 30. And we got to start working on chain, product, and quotient. Question? All right, hold on a sec. Sorry. Yeah. If it's not just x, if it's a function of x, then you've got a composite function, you need the chain rule. It's the rate of change, so it's the chain rule. So it's the rate of change of logs times the rate of change of the interior function. If this was x to the fifth, 5x to the fourth, chain rule, times the rate of change of the interior.